Good afternoon, everyone. Now it's already 2 o'clock. Welcome again to the series of webinar of spectroscopy and chromatography from JASCO Inc. Today we are going to be talking about the circular dichroism. Today our presenter is Dr. Leah Pandisia, who worked at a medical device company as a chemist, and a year later she went for the school in Drexel University, where she got her PhD, and she was working in a spectroscopy lab studying biophysical chemistry. She's a spectroscopy application scientist at JASCO for circular dichroism, UV visible and near infrared, and fluorescent spectroscopy. So now I'm going to pass to Leah, and she can start her presentation.
Okay, thank you, Carlos. All right, so good afternoon, everyone. I hope you're all doing well, and thank you for taking the time to join us today for part one of our circular dichroism webinar. And so JASCO Corporation, or the Japan Spectroscopic Company, was founded in 1958 in Tokyo, Japan, by a Nobel laureate spectroscopist. Today, our headquarters and factory are in Hachioji, Japan, with our Americas office located on the eastern shore of Maryland. While the first instrument developed was an IR spectrophotometer, JASCO now offers a wide range of spectroscopy and chromatography instruments, including circular dichroism, where we have been the world leader in research and production since 1961. Today's overview, or today's seminar, is going to include circular dichroism theory basics, instrument design and components, biological applications, and the relevant CD accessories. The second part of this webinar series will be at a later date, and we'll discuss measurement parameter optimization, sample considerations, and how to acquire good CD data. So what is circular dichroism? CD is the difference in the absorption of left and right-handed circularly polarized light, and a CD signal can be observed when a chromophore is chiral or optically active. And aside from being intrinsically chiral, you can also observe a CD signal when a chromophore is covalently linked to a chiral center or placed in an asymmetric environment. There are a wide range of CD applications, from protein structure to antibody structure, DNA and RNA structure, protein-protein interactions, protein nucleic acid interactions, ligand binding, induced CD, carbohydrate structure, chemical stability studies, thermal stability studies, kinetic studies, stereochemistry, materials characterization, and chiral discrimination and absolute configuration of small molecules for drug therapy and design. So CD is uniquely sensitive to the asymmetry of a molecule, the information, and provides information on molecular and electronic structure. The experiments are relatively quick and easy to perform, and it's a non-destructive technique. So unless you're doing a chemical or thermal experiment where it irreversibly changes the structure of the protein, you can recover most samples to be used for other experiments. It's done in solution phase, so crystallization process could potentially change the molecular structure. However, you can also do thin films in solid phase using a diffuse reflectance accessory. CD experiments are done at low concentrations, so for secondary structure you need about 0.1 mg per mil. So you don't require a concentration which could potentially change the system being studied, which is really nice because other secondary structure techniques such as FTIR use at least 10 mg per mil of sample, which is pretty difficult if you have rare or precious samples or it's hard to purify. So getting into CD, electromagnetic waves contain an electric and a magnetic field components that oscillate perpendicularly in the direction of a light beam's propagation. There are three main properties of an electromagnetic wave: the amplitude, the wavelength, and the polarization. The amplitude is the intensity of the wave from the tip of the crest to the central axis. The wavelength is the distance between two consecutive crests. And the directionality of the electric and magnetic fields is going to define a wave's polarization. So there are a few different types of polarization. In a CD spectrophotometer, unpolarized and linearly polarized light are used to create circularly polarized light, and we're going to be measuring elliptically polarized light of our chiral sample. So unpolarized light, or white light, is created by a light source, and the electric and magnetic fields oscillate in many different directions. In linearly polarized light, the electromagnetic waves oscillate perpendicular to one another along a single plane and are equal in amplitude. So you have one electromagnetic wave along the XY plane in red, and then another along the ZY plane in blue. In circularly polarized light, two electromagnetic wave planes are perpendicular to one another and equal in amplitude, but they are at a 90-degree phase difference from one another, and this plane is going to rotate as the light beam propagates. Optically active molecules can be described by their chirality, or the asymmetry in a molecule's structure. So an example of a chiral object would be your hands, because the mirror image of your hands cannot be superimposed. While an achiral object would be a flask, because the mirror image of a flask can be superimposed. However, most of you listening are spectroscopists, chemists, biologists, physicists, so how does this relate to an actual molecule? So in a chiral molecule, all the substituents bound to that carbon center are going to be different, which is really convenient for secondary structure analysis because the peptide backbone chain, or the amino acid residues of the peptide backbone chain, are chiral. In an achiral molecule, one where you would not see a CD signal, two or more of the substituents bound to the carbon center are the same. So chiral molecules exhibit circular birefringence or optical rotation, where the velocity of light passing through an optically active medium is going to differ depending on the medium's refractive index and rotate the plane of polarized light. CD spectroscopy exploits the fundamental property described by the Cotton effect, or the dependence of CD and on wavelengths. In order to observe a CD signal, an electromagnetic must occur, so CD can only be observed in the vicinity of a chromophore's absorption band, shown here, while ORD, or optical rotary dispersion, the dependence of optical rotation on wavelength, can be detected in the absence of electronic transition, since it's only dependent on the unequal refraction of light. In CD, left-handed circularly polarized light propagates through a chiral sample at a different speed than its right-handed counterpart, and this is circular birefringence, what I had just mentioned. So when a chiral molecule absorbs left and right-handed circularly polarized light to different degrees, the resulting electric field traces out an ellipse. So since linearly polarized light can be thought of as a superposition of equal intensities of left and right-handed circularly polarized light, as circularly polarized light travels through a birefringent material such as a chiral sample, the phase relationship between the circularly polarized light waves changes, and linearly polarized light is rotated, and the elliptically polarized light is now tilted. But how do we even get an ellipse? So the main difference between circularly polarized light and elliptically polarized light is that circularly polarized light is equal in amplitude, and elliptically polarized light is unequal in amplitude due to the differential absorption of the circularly polarized light components. So in elliptically polarized light, there is a difference. If it's a chiral sample, there's a difference in how much the left and right-handed circularly polarized components are going to absorb, and that difference creates this ellipse. And the ellipticity as a function of wavelength defines a circular dichroism spectrum. So how can we visualize this? So on the left-hand side, we have left circularly polarized light that's absorbed to a certain extent. And on the right, we have right-handed circularly polarized light that's absorbed a bit smaller because this is a chiral sample. So you can see as time progresses and the circularly polarized light rotates, the left and right-handed circularly polarized light are absorbed to different extents by a chiral sample. So now, this figure in the middle, we have the blue contribution vector, so that's the left circularly polarized light, and the red arrow is the vector for the right-handed circularly polarized light. And when we add those two together, we get this black line. And as, again, circularly polarized light rotates, time progresses, if you add the vectors of left and right-handed circularly polarized light together, that overall vector traces out an ellipse. So now we get to our instrument. So the principle of measurement is as follows. We have a light source, which creates unpolarized light, which passes through a prism to create linearly polarized light, which passes through a photoelastic modulator to create circularly polarized light, which passes through a sample, and if the sample is chiral, it's going to absorb right and left-handed circularly polarized light to different extents, and then that light is detected by our photomultiplier tube detector. So this is the optical diagram of the J1500. There are 3 models in the J1000 series, which all have, for the most part, the same monochromator. So this empty box right here is the sample compartment. In the J1100, where the actual sample sits is in this area where the monochromator is, so that this is not there. So it's a much smaller footprint. And then we also have a J1700 model. So this is the sample compartment here on the right, which is this empty space here. And then this additional space on the 1700 is holding 3 detectors. So you have a photomultiplier tube detector for UV vis applications. There is a lead sulfide and then an InGas detector for your near infrared applications. So it's a slightly bigger instrument. But in the optical diagram of the J1000 series, and in this particular case, the 1500, you have your lamp housing here with your light source and 2 mirrors, which direct the light into the monochromator through a slit and a mirror to the first prism that chooses the wavelength, through another set of mirrors and slits to the second prism that polarizes the light, through a lens, a filter set to the photoelastic modulator that creates circularly polarized light, to the sample, and then to the detector. So in the CD spectrophotometers, it's a double monochromator, which means it has 2 prisms and a double set of mirrors. And this double monochromator is used to reduce the amount of stray light. So one of the biggest takeaways from this talk is that CD is the difference in absorption. So it's a very small signal. So any effects of noise, since the signal is so small, is going to degrade our signal to noise and have more contributions. So thank you. Stray light is any light that does not fall under the Gaussian distribution at a specific wavelength, and this allows us to measure higher optical densities. So the J1000 series will measure up to 3 absorbance units, or 0.001% transmittance. So very little light at those absorbances is transmitted through the sample. In the far UV, where there's a lot of absorption, we really want to make sure that just our sample is absorbing, and that any additional stray light effects that contribute to the noise are diminished, so we have a good signal to noise. So our light source is a 150-watt xenon arc lamp with a broad spectral output between 160 and 2,000 nanometers and lasts roughly 1,000 hours. Unfortunately, the CD instrument is not portable, and one of those reasons is because we need to purge the monochromator with nitrogen gas. So as is, the instrument sits and the monochromator is filled with oxygen. When you go turn the instrument on in the morning, you want to purge all that oxygen in the monochromator with nitrogen gas. So we do this for 2 reasons. The lamp creates a substantial amount of UV radiation in the far UV. When UV radiation strikes an oxygen molecule, it creates ozone, and ozone is going to oxidize the mirrors. So you have 2 mirrors right next to this light source right here that are going to get a brunt of that oxidation, and they're going to lose reflectivity when they're oxidized. So you don't get as much light throughput into the monochromator, and the less light throughput, the more degradation of the signal to noise you get. The second reason that we want to purge with nitrogen gas is to remove all that oxygen in the monochromator, because oxygen absorbs in the far UV. And since in the far UV, we don't really want to we want to get as much light to the detector as possible. So any absorption that's not from the sample or buffer, we want to completely reduce. So purging the monochromator with oxygen removes any additional absorbance that's not the sample. So the flow rate that you need to purge the monochromator is going to depend on the wavelength range that you are probing. So the further into the far UV you go, the higher the flow rate needs to be. So if you're going above 185 nanometers, so 185 plus, 2 liters per minute is a good rate. If you're going below 180, I would suggest 5 liters per minute. And if you go lower, you're going to have to increase that based on your application. So now we get to light is now in the monochromator. It goes through this first slit to the mirror and to our prism. So the prism is used as a dispersive element for wavelength selection. It doesn't produce a second order effect. It's one angle and one wavelength. And second order effects are a source of stray light. So again, we want to reduce any contributions to the noise. So when when light hits a prism, the speed of the wave changes due to the change in the refractive index from air to the material of the prism, and light is refracted. Different colors or wavelengths of light are going to exit the prism at slightly different angles. So our prism and our slits sit on the same motor. So as the prism rotates based on the wavelengths being selected, the slit is actually going to open or close and adjust based on the wavelength of light selected to allow for that wavelength to pass through to the sample. There is a second prism here in this double monochromator setup, and that also chooses the wavelength selection, but it also is going to create linearly polarized light. So now we get to the lens, and again, we're trying to achieve the most amount of light throughput through this system. So our lens is used to collimate the light to a constant width, because the PMT is going to collect more light if there are 2 parallel beams. Unpolarized light is incident on a birefringent material and splits into 2 rays, an O ray and an E ray. And I'm not going to get into detail, but the difference between the O and the E ray is just due to changes in the velocity at which they travel through the crystal or the material of the prism. So this filter set is going to filter out any of the E ray that could potentially get through the slit, because when we go to create circularly polarized light, we only want 1 ray of light, so there's O ray. So this is very important because in the far UV, you have more dispersion of light. And most common CD application is secondary structure, which is monitored in the far UV. So if there's more dispersion of light there, the slit has to open to accommodate those wavelengths. So this filter set is going to filter out any potential E ray that could get through those wider slits. And now we get to the heart of the instrument, the photoelastic modulator, or the PEM. So the photoelastic modulator is a quarter wave plate which converts linearly polarized light to circularly polarized light. It's about the length and the width of your pointer finger, and it consists of a piezoelastic element, which is shown here in gold, cemented to a block of fused quartz. So there are 2 little wires attached to this piezoelastic element, and that has a voltage, so that applies a voltage to it, to the piezoelastic element, to vibrate it at a specific resonance frequency. So that vibration in the piezoelastic element, since it's bonded to that fused quartz block, it's going to stress and bend the quartz piece attached, which induces birefringence in the quartz. So since linearly polarized light is composed of 2 electric field components, one parallel and one perpendicular to the modulation axis, they're going to travel through that birefringent quartz material at different speeds, effectively retarding one of the waves. So when the quartz is compressed, the polarization parallel to the modulation axis travels faster than the vertical component, and when the quartz is stressed, the parallel component lags behind the vertical component. So basically, it modulates between a left and a right-handed circularly polarized light at different times. So photons that reach the photomultiplier tube detector are incident on the photocathode surface, which releases electrons. So the number of electrons, or these electrons hit a series of plates or dinodes, which is going to amplify the number of electrons. So an electron is going to hit a plate, and every time electrons hit a plate, more electrons fall off. So as they progress through these series of plates, you get an amplification of the number of electrons and therefore the signal. So the output is recorded as the DC voltage or total absorption, and we also get the AC voltage or the CD signal. So again, since CD is the difference in the absorption of left and right-handed circularly polarized light, the signal is very small. And the detector is measuring the difference between left and right-handed absorption. So we want to be able to find this particularly small signal out of all this noise. So we use a lock-in amplifier, which is tuned to the resonance frequency of the PEM, or the voltage applied to the crystal to create circularly polarized light. So now that we have locked into this resonance frequency, we know the modulation of the crystal, so the CD signal can now be detected from a noisy environment. So now I'm going to discuss some circular dichroism applications. And the first is going to be structural characterization of proteins. So proteins are made up of amino acid residues that adopt unique folded conformations that optimize their activity. And information on protein structure is paramount to how proteins function. So circular dichroism can be used to probe the secondary structure, which is the far UV, and it's below 260 nanometers. The tertiary structure, or the near UV, between 260 and 340 nanometers, as well as any prosthetic groups in proteins in the visible region of the spectrum. So the far UV CD is sensitive to changes in the protein backbone bond angles and can be used to estimate secondary structure components. There are 4 different secondary structure components that contribute to the CD spectrum of the far UV, and they're alpha helical, beta sheet, turn, and random coil or unordered, and each component has some characteristic marker bands. So alpha helical structures have the most spectral amplitude and very little spectral diversity, and are characterized by 2 negative maxima at about 208 and 222. This is extremely convenient for samples that require highly absorbing or scattering buffers, which make it harder to obtain good data below 200 nanometers where there's more absorption. Beta sheet proteins have a much smaller amplitude than alpha helical, and they have more spectral diversity, including different twisting and bending orientations of the beta strands. So they have a negative maxima around 215 and a positive maxima at around 195, 200. Turn structures show some peaks around 225 and 200 to 205 and 180 to 190, while random coil or unordered have peaks at 235 and 195 to 200 nanometers. So no protein structure is going to have 100% of any one component, and it is important to note that the spectra that I've shown here represent each structure component as the majority. So what do I mean by that? For instance, the alpha helical example here is myoglobin, and it has about 76% alpha helical content, which means that 24% of the structure is either turn, beta sheet, or random coil. The beta sheet protein here is only 50% beta sheet, and then the turn and random coil spectra are roughly 23 and 55% of their representative components, respectively. So it's really important to note that the characteristic wavelength peaks are ranges, they're not exact values, because these peaks are going to shift in wavelength depending on the component percentages that make up the CD spectrum. And that is going to depend on the protein's interactions and stability. So conveniently, these protein secondary structure components can be quantitatively estimated. So the CD spectrum of a protein can be expressed as the sum total of its CD spectral components, alpha helical, beta sheet, turn, and random coil, multiplied by their respective abundance ratio. So this term here is going to be the entire CD spectrum at the wavelength range you're looking at. You then have the ellipticity or the CD wavelength for each secondary structure component. So alpha helical, beta sheet, turn, random coil, and unordered. And then this F turn is going to be the fraction of each secondary structure that's multiplied by the ellipticity of each term. So the secondary structure abundance ratios, or the fraction of the secondary structure, Those are determined using different component analysis and regression techniques to ensure the minimum distance between measured and calculated spectra. So first, the calibration model has to be created to compare the measured spectra to. So X-ray crystallography data provides the known secondary structure percentages for a given protein sample. This X-ray crystallography data can be found in the protein database, or if you have access to an XRD, you can acquire that crystallography data yourself. A CD spectrum of that exact protein sample is then obtained, and then using principal component analysis, or partial least squares in the case of our program, the calibration model constructed is used to estimate the unknown secondary structure of a measured protein spectrum. So the figure on the left here shows the reference set template of our CD spectra using the multivariate secondary structure estimation program, and it consists of 26 reference proteins. And then the figure on the right is the actual secondary structure estimation program. So on the right top here, we have the unknown measured CD spectrum. In the middle, we have the component fit to that unknown CD spectrum. And then on the bottom, we have the error between the measured unknown CD spectrum and the total fit. And then on the left here, we have this table is the actual secondary structure estimations or percentages for each uploaded spectrum. So in this application, dilute sulfuric acid was titrated into a polyglutamic acid sodium solution, and the changes in the secondary structure were quantified. This figure on the left shows that as dilute sulfuric acid is added to the peptide sample, the peak below 200 nanometers increases and the peak above 200 nanometers decreases in intensity. On the right, we have the secondary structure, the abundance ratios, as a function of the sulfuric acid concentration. And as the peptide solution becomes more acidic due to the addition of sulfuric acid, the alpha helical ratio is going to increase, which is shown in blue, concomitantly with the decrease in the random coil structure. So the near UV CD spectrum of protein solutions probes the tertiary structure, which is composed of aromatic amino acid residues, tryptophan, phenylalanine, and tyrosine. So factors that influence the near UV spectra are changes to the solvent environment in the disulfide bonds, interactions of the aromatic amino acid residues with this solvent environment and with one another, the rigidity of the protein, so changes in the interaction dynamics of those aromatic amino acid residues in their solvent environment. And then the number of aromatic amino acid residues in the protein is going to influence the spectral amplitude. In this application, apo-alpha-lactobutane was denatured using 3.44 molar guanidinium chloride, which is shown here in green. The spectral changes suggest that the aromatic amino acid residues, which are here in red, in the interior of the protein were exposed during denaturation, unfolding the protein. So the blue spectrum is the non-denatured folded protein, where the green is the denatured unfolded protein. Sorry. And the reduction in the CD signal indicates the aromatic residues are no longer in close proximity to one another and can no longer couple as strongly, decreasing the CD signal. Here are some denaturation curves for an alpha-lactobutane probed at 270 nanometers and 222, which correspond to the tertiary and secondary structures of respectively. The curve at 270 shows the protein transitions from a folded to an unfolded state at a lower guanidinium chloride concentration, indicating that the tertiary structure unfolds prior to the secondary structure of the protein. So now I'm going to go over an antibody stability evaluation. So antibodies are more and more attractive for drug therapy because they do little damage to the body since they're proteins and can be used for various drug targets. So VHH antibodies are heavy chain antibodies corresponding to variable IgG domains. They are highly stable with respect to heat, pH, and denaturing agents. They have a high affinity and specificity. They have low molecular weight, which increases the mass production efficiency. They have a unique binding capacity to small cavities, and they are highly soluble and easily modified. The effects of ambient environmental factors, such as temperature, pH, salt concentration, may cause antibody drugs such as VHH and IgG to undergo a change in their higher order structure so that they lose their activity and function. And therefore, the structure stability with respect to ambient environmental factors must be evaluated. So the structural changes of VHH were looked at using a high throughput CD system, and the changes quantified with our Spectrum QC test program. The HT-CD system automates sample measurement, aspiration, and flow path washing and drying for up to 192 samples. And the Spectrum QC test program then evaluates whether the changes in the spectra are statistically different from a specified reference set. The Spectrum QC test program first creates a reference set of the native or fully folded molecule CD spectra in order to define boundaries and spectral variation. The difference in the unknown and reference set spectra are then squared and divided by the standard deviation of the noise of the unknown spectrum. This weighting step accounts for instrument noise at shorter wavelengths, which is larger due to less light throughput. So change is evaluated as small where the noise is larger and larger where effects of noise are smaller, so that slight changes in sample differences are detected with high sensitivity. And in the last step, the difference between the reference set and the unknown spectra at varying wavelengths is quantified. So the CD spectrum of VHH at various pH and salt concentrations was measured, and shown here is the spectra at varying pHs. So you can see at pH 3 and 4, the beta sheet peaks at 217 and 227 change in CD intensity, and at pH 11, the characteristic VHH peak at 235 decreases in intensity. So this plot quantifies the changes in the CD spectra. The Z-score describes how many standard deviations the spectra are from the reference set average. The larger the Z-score, the greater the distance or difference between the native and measured spectra. The Z-score is small at pHs 6 to 9, and the structure is not significantly different from the native sample at pH 7 and a concentration of 200 millimolar salt, which would be shown here. You can't see anything because that Z-score is 0 because it's identical. On the other hand, at pH 5 and lower, or pH 10 and higher, the Z-score is large, indicating that the structure is significantly different from the reference. And you can also see that with increasing salt concentrations, the secondary structure changes as well. So thermal stability studies. Thermal stability measurements are used to monitor structural changes and reversibility of sample folding due to changes in temperature. So by fitting thermal denaturation curves, information on thermodynamic parameters such as the Gibbs energy, melting or denaturation temperature, and changes in entropy and enthalpy can be determined. So first thermal melts were acquired by monitoring VHH's CD signal at 217 nanometers using our multi-position Peltier cell holder. To determine the reversibility of the melt, the temperature was repeatedly raised and lowered from 25 to 50 degrees Celsius, and the CD was checked at 25 degrees for any changes to the signal. The same measurement was carried out for 25 to 60 degrees, 25 to 70 degrees, 25 to 80 degrees, and 25 to 90 degrees, and the denaturation temperature was determined to be 67.5. The temperature-dependent spectral scans were then measured, and the figure on the left shows the CD spectrum from 25 to 50 degrees, where only slight changes in the protein occur. The CD spectrum on the right show the changes from 25 to 90 degrees and illustrate significant changes to the peaks at 217, 227, and 235, indicating changes to the secondary structure. We then quantified changes in the spectral scans to elucidate a better understanding of the changes in the protein structure. So this figure here shows the relationship between the number of temperature increases and decreased cycles and the spectral distance, or the Z-score. So at 50 degrees, the slope increases sharply from the 16th cycle, indicating that the structure changed as a result of repeated increases and decreases in temperature, even though 50 degrees was lower than the denaturation temperature of 67.5. So this study illustrates the importance for checking how temperature affects the reversibility of antibody structure when manufacturing modified antibodies. So DNA and G quadruplex structure. So DNA is another common application for CD and one of my favorites for the following reasons. So DNA is made up of 4 base pair units that are achiral. The base pairs are covalently bound to some achiral phosphate groups, so they're achiral, no fun. But they're also covalently bound to some chiral sugar groups. So we can therefore measure the CD signal from the chiral sugars that's induced into the electronic transition from the base pair units and acquire a CD spectrum of DNA between 200 and 300 nanometers, which is the pi-to-pi star transition of those base pairs. So CD is typically used to determine DNA polymorphs. So the CD is going to vary more with the base orientation than the DNA sequence. And there are 3 polymorphs. There's an A form, a B form, and a Z form. And each form gives rise to a slightly different CD spectrum. We also have G quadruplex structure. So G quadruplexes are a type of DNA structure where 4 guanine bases form a planar structure with 2 or 3 of these stacked on top of each other. And then there are metal ions that are present between the layers, and if the type or concentration of these ions changes, the structure and activity can change as well. So there are 3 different types of G quadruplex structures: parallel, hybrid, and antiparallel, and they each have a characteristic CD spectrum. So any environmental changes, temperature, chemical mutations, metal ions, are going to induce a different CD spectra in these G quadruplex structures, so they could be monitored as well with CD. So spot flow CD. Spot flow is used to observe fast reactions occurring on a sub-millisecond timescale. So 2 or more solutions are loaded into a set of syringes, and the flow is stopped, and the progress of the reaction is measured by CD, and the reaction rate constants can be determined. So here we followed the refolding of cytochrome C by adding a buffer solution to an already denatured protein solution. So by measuring wavelengths in the far and near UV spectra at 222 and 289 respectively, we're able to monitor both the secondary and the tertiary structure of the protein to determine the refolding order. So we want to know, does the secondary or tertiary structure fold first? Which one is more stable? So using the time course data shown here in our reaction rate software, we're able to calculate the reaction rate constants for each measurement. And using these reaction rate constants, we can determine that since the near UV data, tertiary structure, have a smaller rate constant than the far UV data, or the secondary structure, this indicates that the tertiary structure of the protein is going to refold slower than the secondary structure. And last but not least, we go to some micro-assay methods. So a typical 1 millimeter path length cell requires roughly 250 to 400 microliters of sample, depending on if you need to fill the entire cell. So there are numerous circumstances that are going to require much smaller sample volumes for rare samples. So the micro-sampling disc on the top left here allows for spectral measurements using 2 to 10 microliters of sample depending on the path length. And there is a 0.2 and a 1 millimeter path length option, which corresponds to about 1 microgram of sample. So to use this, a sample is placed on the quartz disc using a micropipette. There is a cover, so there's a glass slide in that cover, and that cover is screwed onto 2 pins here, and the micro sampling disc is then placed in the standard cell holder, of the sample compartment. The figures on the right here are showing the microsampling disc in blue and the cylindrical cell in green, the great signal to noise that they exhibit, and also you can barely even see the cylindrical cell data because the overlay is so great. If you're interested in microsampling and doing thermal studies, we have a capillary cell and cell jacket holder, which has a 0.5 millimeter path length and holds roughly 10 microliters of sample, or 10 microliters and roughly 2 micrograms of sample. So how this works is sample is drawn into this capillary cell, and the end of the capillary cell is sealed with sealant. And this blue would be the liquid that was sucked up by the capillary cell, and the white is that sealant. And then that capillary cell is placed in this cell jacket, which is then placed into a Peltier, either the single or multi-position Peltier cell holder. So the figure on the right shows a thermal melt using the rectangular cell. So that's a standard 0.5 millimeter rectangular cell, which is going to hold maybe 200 microliters of sample. And the green line is the capillary cell, which is going to hold 10 microliters of sample. And while the signal to noise of the capillary cell is lower than the rectangular cell, this is because if you can see in the cell jacket, that is the aperture for the capillary cell. It's much smaller than a traditional rectangular cell, so there's less light throughput. However, the overlay of these two curves is fantastic. So you can still get denaturation data using the capillary cell and potentially get thermodynamic parameters off of this study. So with that, there's some educational resources I want to bring up. As Carlos mentioned earlier, our next webinar is going to be on VCD theory and applications next Tuesday at 2 p.m. And we have some more webinars, FTIR theory, instrumentation and techniques, FTIR microscopy. I'll be doing the second circular dichroism measurement optimization webinar, a Raman microscopy and imaging, and SSE theory and applications. We also have some great resources on our website. We have ebooks and tips and tricks posters that we can send you on Raman, fluorescence, FTIR, and CD. And then near and dear to my heart is our knowledge base, which is basically a database of peer-reviewed papers using JASCO instruments. So if you want to see if there's an application and someone is potentially published on it, you want to see some data on it, understand how they did experiments, you can go to this database, type in your keywords, and find a whole variety of papers using CD or Raman or anything from JASCO. So with that, I want to thank you for attending our CD webinar part 1. And if you have any questions, I'd be happy to answer them.
Well, thank you, Leah, for that amazing webinar. With that, we are finishing her presentation. Now we are open for questions. We already have one here.
Okay. Okay, can we have different slit widths for a single read? I'm assuming that that question is asking because there are 3 different slits, if you can, or if maybe you can vary it as you're scanning. The answer is no, there's only one slit width you can set. So unfortunately, yeah, we can't really do that. How long does it take to do a measurement? That is 100% going to depend on the wavelength range you're probing, the digital integration time, and this is going to be a lot of measurement stuff that I'll get into in our next webinar. But if you're doing secondary structure and you're just doing one accumulation, it takes about 40 seconds. So I would say that maybe if you're doing a little bit more than secondary structure, I don't know, I'll estimate a minute, but again, it's really going to depend on the parameters you're using and where you're looking. I believe we will have this presentation available for download. Another question. If I'm not acquiring data in the View V, do I still need to purchase nitrogen? Okay, so we actually offer an ozone-free lamp. So if you are not doing secondary structure measurements, if you don't need to get below 200 nanometers, we offer a lamp where you don't need to purchase nitrogen. However, you really can't go below 200. So for anyone doing applications in wavelength ranges above 200, you can talk to either, if you already have an instrument, your service engineer, your CD rep, or you could also ask me and we can try to give you something for an ozone-free lamp. what does it matter what buffer system I'm using? It definitely does. You want to, and I'll go into this again in the next webinar, but you definitely want to avoid using any salts if you can, because that's going to scatter and introduce noise into your signal to noise. You want to, if you can, nothing that has a CD signal first off, so no sugars. If you can avoid using any highly absorbing buffers, if you're going to use, say, a phosphate buffer, just use a smaller concentration. But I'll have a whole bunch of charts for that, which you can visualize instead of me just explaining in a couple weeks. So you definitely should be able to do RNA structure with CD. If you have some questions about, so is it feasible to measure RNA structure, or is it too unstable to generate a measurable signal? You can definitely do RNA with CD. If you have questions about your particular system, if you want to shoot me an email, and I think we will be sending out emails for everyone that attended this seminar with my email, so that if you have additional questions that are very specific, I can answer them. Can I run multiple samples in cuvettes? Yes. So I think, so there's a couple things, a couple ways I could answer this question. So if you have a multi-position Peltier, then we have a 6-position, so you could do 6 different samples, one right after the other. If it's a single position Peltier, you can still do, you can run multiple scans of a single sample with one of our cycle functions. And that's something I would kind of have to show you guys in our software, but I can definitely add that for next time. Do you have software to help quantify secondary structure of proteins? Is there anything similar for quadruplexes? Great question. We do have software to quantify secondary structure of proteins. It's called the Multivariate Secondary Structure Estimation Program. The other thing I forgot to mention is we have videos on our website which go over a lot of the different software measurement programs and processing functions. So two of the videos on our website go over our secondary structure estimation program, how to build a calibration model, and then how to do the actual secondary structure estimations. So if you already have our CD instrument, you can reference those videos there. And if not, then it's definitely, if you purchase a CD instrument, the CD secondary structure estimation software automatically comes with it, as does all our CD software, which is really nice. And in relation to that, can you add, I'm sorry if I'm talking really fast, can you add CD spectrum to the reference set? So does the template come with the software? So the secondary structure estimation program. So we give you a template, which does come with the software. You don't have to purchase the software or the template separate from the instrument. That's all one package. The template for the secondary structure estimation program comes with 26 reference proteins. You can remove some of those reference proteins, and you can also add to those reference proteins. You can also create your own reference set if you have access to X-ray crystallography data, or if you just want to grab proteins off the PDB and then run a CD spectrum on them yourself and add those to a reference set. You can do either. So you can edit it, and then you can also create your own. Yes, you can measure the melting temperature using CD. You would basically just do CD as a function of temperature. And then we actually offer a software program which will calculate that melting temperature for you as well, given it's a single transition. Can you do fluorescence and absorbance on the same instrument? Yes. So we have our instrument measures, and I'll kind of go into this again in the other seminar, but our instrument does measure CD and absorbance simultaneously. And if you get the fluorescence monochromator accessory, you can also do fluorescence either simultaneously with CD and absorbance, or you can do that as a standalone. However, I'll make this note that we also do sell fluorometers, and my coworker Sherry Hemmingson gave an excellent presentation last week on it, which I believe you can still have access to, or shoot me an email and I can try to get you the PowerPoint for it. Sorry, I'm trying to scroll through these. Is a little bit of cloudiness okay if the solution is clear? I'm not entirely sure what that would mean, because if it's cloudy, then I'm not sure if the solution would be clear. I mean, if you have cloudiness in the sample, I'm either going to assume it's because you can't purify it further. A little bit of cloudiness, actually, if you're doing a temperature study, might be because you're getting some particulate particles that are aggregating. So you want to be a little careful about that, because you don't also want anything to crash out of solution, and then you're actually not measuring the CD of your entire solution, but just potentially the buffer at that point if the entire sample crashes out. But let's just go with, is cloudiness okay in the solution? Yes and no. So if you have cloudiness, it could be because there's particulates in there. It probably is because there's particulates, which mean that the light is going to scatter, which means that your signal to noise is going to be reduced. However, you can still get a good CD signal, and you just would have to optimize your parameters a little bit better to account for the signal to noise. Oh, I'm sorry. There was also a question about G-quadruplex estimation programs. We don't have a G-quadruplex estimation program. I don't believe there is a software program to quantitatively estimate G-quadruplex structure out there currently. I do believe there are some research groups that are working on it, but to my knowledge, it's not currently, it hasn't gotten to the point where you can quantify stuff like secondary structure. Oh, goodness. What is the best way to handle sample scans that have protein and DNA? So that's a loaded question. So that's kind of tricky, because you have, protein and DNA are kind of going to absorb in the same region. With protein, I'm assuming you're looking at the secondary structure of that protein. So you kind of have a little bit, I guess you could hope that your DNA structure has more, I'm not sure what type, if it's a quadruplex or what sort of polymorph it is, but hopefully it has a bit more structure at the higher end of that region, where you can kind of pick that out from your protein secondary structure. But that's a really great question. I was just talking about this recently, and it's kind of hard to deconvolute when you have either two protein interactions or even a protein and DNA interaction without potentially mutating something. So you could shift it off wavelength. So I don't have the best answer to that currently. What is the difference between the J810 and the newer versions of the instrument? Probably the biggest difference are, if you do any sort of temperature studies, the temperature, the accessories for your temperature dependent studies are now all integrated into the instrument. So for the J810, you had a power box, and the Peltier that sat outside the instrument, they now sit inside the instrument, so you don't have anything on the outside. So it's a much shorter, smaller footprint. The signal processing software is different as well. I would, off the top of my head, those are the two main differences between our older software, or our older instrument and the newer instrument. There are definitely some software upgrades with the 1000 series. what is the golden buffer for CD? I think I'm going to interpret this as what is the best buffer to possibly use for CD. Well, my first part of me wants to say water because there's no CD signal. But I guess the best buffer would be the one, if you're looking at stability, you really want what your sample's most stable in. My biggest takeaways for choosing a buffer for CD, if you're going to go with something, just go with a maybe 25 to 50 millimole phosphate buffer, sodium phosphate buffer. If you can make the phosphate buffer yourself, I would suggest doing that. I have had some experience with saline buffers that you can buy pre-made from Sigma or something. You can definitely dilute those because I think they come in a 1 molar concentration, but you tend to get better signal to noise with a sodium phosphate or potassium phosphate buffer that you potentially make yourself. Is there a relationship between the signal detection and the wattage of the lamp? So no. This is something I'm going to kind of go into in the next webinar about the HT voltage and how that accommodates for fluctuations in light level. In regards to, I feel like this is kind of related to how do you know when to change the lamp? Is your lamp, I mean, I suggested that you change the lamp every 1,000 hours. Technically, it can go out to 2,000, but you're going to get less light throughput of the lamp as that progresses, which could potentially bring down your signal to noise. There is a way in the software, if you go in the spectrum measurement program, where you can actually check the lamp hours and it will tell you, or you can also go into the admin properties and have a pop-up that tells you when your lamp hours have reached a certain amount of time. Can I use CD to test the thermostability of very short peptides like 7 residues? You most certainly can. I personally have done research on tripeptides. My old research group does research on tripeptides. There's a lot of research using CD on different short peptide segments. You can do CD, you just have to keep in mind that because you have much smaller residues, the signal to noise is the signal is going to be a lot smaller, so you just might need to do a lot more accumulations, and you need to just really optimize your parameters there. Can you perform measurements on protein samples and formulation buffers? You can, you just have to be careful because you're probably going to get a lot of absorbance from those formulation buffers. Some of those formulation buffers might have a CD signal, which is going to be tricky. But you just have to, if you can potentially purify something further or dilute. If you have your sample in your protein formulation buffer, if you could potentially dilute that, so if you have a higher concentration, if you dilute the sample to the desired concentration required for CD in a non-formulation buffer, that would be another way to kind of work around having any highly absorbing formulation buffers. Okay, I already did the ozone free lamp. CD is an absorption technique. To the question about is CD based on absorbance or scattering? I think. How pure does the protein sample have to be? That's also going to be kind of, I'm not sure if you mean by like, if it can be a mixture of proteins or pures in the sense of, you have different buffers or different chromophores in it. Basically, you want it, if whatever chromophore you're probing, so if one single protein is what you are interested in looking at, then if you can purify that as much as possible, great. I understand that there are going to be limitations, so it's kind of just what are your limitations, what can you work with, and I mean, there are sample itself considerations to take into account, so preparations of the sample, and once you've, you know, really, I can't think of the word, gone to all extents that you possibly can to purify or optimize your sample prep, and you can't do anything else, then we're going to look at measurement parameters and what we can do to optimize the sample now with any measurement parameters we have. And then if the formulation buffer of antibody contains chiral components, can these be diluted out rather than fully removed? Again, I think it kind of just comes down to where you can only do, everyone's going to have a limitation, so you can only do so much. So if you can only dilute it rather than fully remove it, then I will always tell people to try what the absolute end to what they can do, and then just run a sample, run a spectrum, and see what you get. And if you get something that's usable, has a good signal to noise, then great. You don't have to worry about doing anything else if you can't do anything else. And if not, then we kind of go back to the drawing board. But it's hard to give an overall over-encompassing answer to some of these questions just because it's going to be sample dependent. However, hopefully my answers provided a source of hope if you didn't think you could do CD with some of your samples, or just the fact that you can try different things. I mean, that's the great part about doing science, is experimenting.
Okay, well, Leah, thank you very much. I think that you answered a lot of the questions. I'm sorry there are still questions popping up. We designed to this webinar for 1 hour. We have record of all questions, so we are trying to think what to do with this question, either share with all the audience or answer directly to each person, but definitely we want to address any comments. So again, thank you, Leah. Thank you, everybody, for spending this time with us. And remember, there are more webinars coming, and they are going to be posted in our LinkedIn page. So that is one of the ways to register to our coming webinars. You can email me. And well, I have to say thank you, everyone, and have a good afternoon. Thank you.
Thank you.